How are we going to figure out whether you're dealing with a conservative force or a non-conservative force? Well, as we've seen earlier, if you're dealing with conservative forces, then the change of potential energy plus the change of kinetic energy must be equal to zero. That is, if you have a system which evolves from a state 1 to another state 2, most likely in time, then all you have to do is figure out all the forces present at both times. And once you have allocated all the forces, you can write down all the potential energy. So if you start with this term, you're going to add all the potential energy at that particular state. And then you're going to add the kinetic energy at that particular state 1. Then you're going to do the same thing at T2, or in a state 2. You're going to add all the potential energy, and this time all the kinetic energy. And then you're going to add them up, and then you're going to set those two equations together, equal to each other. And if you have the same number on the left hand side as the number on your right hand side, then you know you're dealing with conservative forces. If those two numbers don't add up, then you know you have to add another term which will represent the potential due to the non-conservative force. That's the first way. Another way to figure out if you're dealing with a conservative force is to calculate the work. If you calculate the work between 1 and 2 along a particular path, if you calculate the work along a path from state 1 to state 2, and then from state 2 to state 1 again, then you should end up to 0. If you're not ending up to the 0 value, then you know this is a non-conservative force. So let's say you're bringing a ball from a particular position to a new position. You calculate the work for this path, and then you want to calculate the work from this situation or this position back to y1. You calculate the work for that path again. When you add them up, if you end up with 0, then you know you're dealing with a conservative force, which would be the case for the weight. And if you do the same process and you end up with a non-zero value, let's say for friction, then you know you're dealing with a non-conservative force. The third method to figure out if a force is conservative or not is to just calculate the curl. And if you end up with a 0 vector, then you know you're dealing with a conservative force. If you have a non-zero value after taking the curl of that force, then you're dealing with a non-conservative force. So let's review a little bit that idea of curl. Remember that we defined the potential as dV being equal to minus sum of the forces F dr. Let's take the case of one force. So you're dealing with a force, you take the dot product of that force with the path dr, take the minus of it, and you end up with a potential. Now remember, we define the existence of this V as a scalar function, which has to be because on the right hand side you're taking the dot product of two vectors. So let's do this in Cartesian. And you can do the same thing in polar or cylindrical, spherical, whatever. So if dV is a scalar function, then it might be expressed as the function in terms of the x, the y, and the z coordinate. So dV can be written as partial derivative of v with respect to x dx plus dv dy dy plus dv dz dz. And this must be equal to minus FDR if it exists. Now we can do the same thing and try to evaluate this in component notation. Let's imagine you can write your force in component notation, which is Fx I plus Fyj plus Fz k. dr can be written as dxi plus dyj plus dzk. So if you take the dot product of f and r, then I dot I will give you 1, I dot j will give you 0, I dot k will give you 0. So you end up with only having 3 terms. First term will be this one and this one, fx dx. The other surviving term is fy dy, and the last term is fz dz. Or the other term will be 0 because I dot j is equal to 0, I dot k is equal to 0, j dot I is equal to 0, j dot k is equal to 0, etc, etc, etc. So, if we can't find such a function defined by this, then this must be equal to minus this. So the terms in terms of dx must be equal to this one. So this one must be equal to minus that one. And then this one must be equal to minus that one, etc, etc. So we end up with 3 equations. Fx must be equal to minus dv dx. Fy must be equal to minus dv dy. And Fz must be equal to minus dv dz. So we can generalize this with the del notation. This is the del notation. I think it's also called nabla. So if you look for it on net, you either type del or nabla. And this is defined as partial derivative with respect to x plus partial derivative with respect to y, partial derivative with respect to z. So this is called the del operator, and when you apply the del operator to a scalar function, you end up with a vector. So you have a scalar function v, you apply the del operator to it, and you end up with a vector function. So technically, I should put this in too. And when you apply the del operator to a scalar function, it's also known as the gradient, which is related to the derivative. Well, of course, you're taking the first derivative with respect to x of the x term, the y derivative with respect to y of the second term. Remember that the partial derivative only means that, let's say for the first case, if you take the first term's derivative with respect to x, you have to hold y and z constant. What if you take on the second term, the derivative with respect to y, you have to hold x and z as constant. That's what partial means. Okay, so keep that in mind. The important thing about gradient is that if you take the gradient of a scalar function, you end up with a vector function, which is expressed by this. Now there is other ways that you can use that operator, the del operator. You can apply this operator del to a vector function, f. In this case, it's known as the divergence. So all the I of your del will be dotted with the I of the x of the f. All the j of your del will be dotted with the j of your f, etc, etc, etc. So you can guess what would be the answer. It has to be a scalar. So whenever you apply the del operator to a scalar function, you end up with a vector function. And whenever you apply, and that's called a gradient. Whenever you apply the del operator with a vector function. It's like taking the dot product and you end up with a scalar function. So in this case, you will just end up with ddx of fx plus ddy of fy plus ddz of fz. This is useful for forces or field that are diverge. So if you have, let's say you're dealing with gravity or spring or electric field, then it makes sense to calculate the divergence because that's how your field behaves. So you will end up with non-zero value. Now there is some forces that don't behave like this. There are some forces that instead of behaving like this, behaves like that. What they do is they curl. So an example of this would be the B field. So to deal with such forces, you can use the del operator in another way. Instead of now taking the dot product with the del operator and your function, you take the cross product. And that's called the curl, which in this case is very similar to the standard cross product I used to, and therefore can be expressed like this. You put the del operator here, ddx, ddy, ddz, you put your forces here, fx, fy, fz, and you can take the cross product as you usually do. The I component would be ddy times fz minus ddz times fy, and so on and so forth. So we end up with three terms, and of course this is a vector function. So when you take the curl of a function, you end up with another function. Now if the results of this operation gives you a zero vector, then you know that you have no curl. And this happens to be an indicator of conservative forces. So conservative forces don't curl, or the curl of the conservative forces is not zero. So obviously the B field is not a conservative force. Now there are several properties that might be useful later on. If you take the curl of a function, so del cross f, and you happens to want to take the divergence of this, now this, remember, gives you a vector. So you need to use the dot product if you want to apply the del operator again. So d dot d cross f will always give you 0, and that's a scalar. Again, this is a vector. Now you take the dot product between a vector and another vector, well, an operator and another vector, you end up with a scalar. So that's the divergence of a curl. Now you can do the same thing if you have the gradient of a function, which, as we've seen, is a vector. Let's say you want to take the curl of that vector. You should end up with 0 again. So again, this is the del operator applied to a scalar function f. You take the gradient of that function, you end up with a vector. And then you take the curl of that vector, and you end up with a vector again. In this case, it must be the 0 vector. So this is always true, this is always true. Another one that's quite useful is if you have the gradient of a function, which is also a vector, and instead of taking the curl, you're going to take divergence of this vector. This is known as the Laplacian, which is very useful and comes back when you deal with the Hamiltonian of a system. An example is if you start playing with Schrödinger's equation, where you have to deal with the Hamiltonian, then it will show up all the time. So this is a very common operator, which is nothing else than just the same as the gradient, but doing it twice. And that's a scalar, I'm sorry. because this is a vector, you take the dot product between a vector and an operator, you end up with a scalar. So really the Laplacian is nothing else than taking the second derivative of a function, which obviously has to be a scalar function. So you can get or the functional form of your del operator on Wikipedia. You just type del or nabla and something like nabla cylindrical spherical on Wikipedia, and you will get the functional form of your del operator in Cartesian, which is the one that we've been using, ddx, dy, ddz. You will get the version in Porter, which might be useful for 271, and you will also get the version in cylindrical if you want to. So again, remember, 3 ways to figure out whether a force is conservative. You can just take the curl of that force, or you calculate the work for a path that is closed, or you apply the energy conservation, and if you don't end up with a 0 value, then you know that there is a non-conservative force present.